Problem number 18. Solve these inequalities, expressing your answers in interval notation. And these aren't just linear inequalities. I think we saw those well earlier in this problem set, but these are going to be, have quadratic polynomials in them. So let's just take a look at the first one. Our goal should be to factor this, and it's pretty easy to see that this factors as x minus 1 times x minus 7, and we want this to be non-negative, greater than or equal to 0. And so the thing that we should realize is that we want, when is this non-negative? It's when either both these terms are positive, and when I'm saying positive here, I mean non-negative, but it's a little bit easier, just put a plus sign for positive, or if they're both negative. So we want both of them to be positive or both of them to be negative. We don't want one to be positive and one to be negative. So let's just draw a little number line here. So x minus 1, that's 0 at 1. X minus 7, that is 0 at 7. And so we see that if we are bigger than 7, both the x minus 1 and x minus 7 terms are going to be positive. If we're less than 1, both the x minus 1 and x minus 7 terms will be negative, and in between, one will be positive and one will be negative. So we see that where is this non-negative? It's in two separate intervals. One interval from minus infinity to 1, and one interval from 7 to infinity. So our answer is going to be the interval from minus infinity to 1, union, interval from 7 to infinity. Now you notice here I've intentionally left off putting the brackets here yet, because we just have to check this is a greater than or equal to. When x is 7, the left side is 0, and that satisfies the inequality. When x is 1, this side is 0, and that also satisfies the inequality. So we include those inside in these intervals. Okay, so that's the first one. The second one is similar. Let's move, we just have to rearrange things a little bit. Moving that 3 to the left, we get 2x squared minus 5x minus 3 is, now we want it to be negative here. And so let's factor this. To find factors, we can realize that 6 times 1 also equals 2 times 3. So I'm going to break this up as 2x squared plus x minus 6x. I'm rewriting minus 5x as x minus 6x. Minus 3 is less than 0. So this will allow me to factor things. From these first two terms, I can pull out an x times 2x plus 1. And from these terms, I can pull out a minus 3. And so we get 2x plus 1. And so what do we see here? This is 2x plus 1 times x minus 3 is less than 0. So similar to before, we want now, instead of having both the terms be positive or both the terms be negative, because we want this to be negative, we want exactly one of the terms to be negative. So when does this happen? Well, this is equal to 0. X is equal to minus 1/2. This is equal to 0. X is equal to 3. So minus 1/2 to 3. And so exactly one of these terms is positive and one of the terms is negative in between. So between minus 1/2 and 3, this term would be positive and this term would be negative, and we get positive times negative gives us negative, which is what we want. Note this is a strict inequality, so we don't want to include the endpoints here. So our interval is minus 1/2 to 3, open parentheses. Okay, so finally, 3x minus 1 divided by x minus 4 is greater than or equal to 0. And so one more time, we want both the numerator and denominator to be positive, or both the numerator and denominator to be negative. So I'm just going to draw two separate number lines here. So the numerator is 0 when x is 1/3. The denominator is 0, x is equal to 4. So the denominator is going to be positive if x is greater than 4. It's going to be negative as x is less than 4. The numerator is positive, x is greater than 1/3, and negative if x is less than 1/3. And so we can see we want, again, the numerator and denominator to have the same signs, both positive or both negative. So bigger than 4, they're both positive. Less than 1/3, they're both negative. So we're going to have minus infinity to 1/3, and 4 to infinity are going to be the intervals. So minus infinity to 1/3, union 4 to infinity. And so the last thing that we have to do, just as earlier, I've left off drawing a square bracket or open parentheses here. So we just have to check the endpoints. So when x is 1/3, the numerator is 0. The denominator is not 0. So 0 is greater than or equal to 0. Yes, it is. So we include that. But when x is 4 here, the denominator is undefined. So it's not in the domain of our of this expression here, this function here. So we don't want to include it, and we draw an open parentheses there. Okay, so that's problem 18. So I'm solving some, more interesting inequalities than earlier in this problem set. For problem 19, there's going to be one exponential function and one logarithmic function, and the instructions are the same in both cases. Sketch it. What's the domain? What's the range? What are the asymptotes? What are the intercepts? So let's just kind of take these in whatever order is natural to do. So f of 0, when we plug in 0 here, it's going to be 3 to the 0 minus 2 plus 4. So 3 to the 0 minus 2, that's 3 to the minus 2, is 1/9. So this whole thing is 1/9 plus 4, and that should be 37 over 9. And so this actually, so let me start drawing a sketch here. So 37 over 9. My marker is a little bit thick there, it's hard to read here. And then this is actually, so y-intercept is 37 over 9. That's just what value you get for f of 0. So what does this look like? As x gets bigger and bigger and bigger, this goes off to infinity like this. But as x gets smaller and smaller and smaller, 3 to the x minus 2, this gets closer and closer to 0, so the entire expression gets closer to 4. So there's actually going to be an asymptote here at 4 that it's approaching. My scale's off. Obviously, 37 over 9 is just 1/9 bigger than 4, so those two really should be close together. I'm drawing them a little bit further apart just so that we can more carefully see what's going on here. So the only asymptote is that y is equal to 4. And we see that our function never becomes negative, so there's no x-intercept. Okay, so we've got our sketch, we've got our asymptote, only asymptote is y is equal to 4. We've got our x-intercept here, which doesn't exist, or y-intercept is 37 over 9. So the only thing left over is domain and range. So the domain is going to be all real. So we can plug in any number we want to into here, and life is good. So we can write it in interval notation we want to in that way. The range, what are the allowable outputs? It's all y values that are strictly bigger than 4. So the range is going to be 4 to infinity. So we never get to 4. So no matter how negative x gets, 3 to the x minus 2 is going to be positive. It's going to be very, 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 very close to 0, perhaps, but it's going to be strictly positive. So a little bit bigger than 4. So range is all numbers that are bigger than 4. Okay, so that was an exponential function. Let's now do a log function here. So let's see here. Same set of problems. Y-intercept is maybe the easiest one to start with, because that's just f of 0 is log base 10 of 0 minus 1 plus 2. But our alarm bell should be going off, because we can never take logs of negative numbers. So this is actually undefined, that there is no y-intercept. And in fact, what is the domain? So here we have to be careful with the domain. It's going to be, we want x minus 1 to be strictly positive. So the domain is x is strictly bigger than 1. In interval notation, it's 1 to infinity. So when I draw some axes here, so there's 1. So there's actually going to be an asymptote here as x gets closer and closer to 1 from the left. This is what, it's going to go off to minus infinity. So this is what the graph of this should look like. So we've got our sketch taken care of, we've got the domain. The range actually is going to be all reals. Asymptotes here, it has one asymptote at x is equal to 1. It's an asymptote. And the last thing we want so we said there's no y-intercept. What's the x-intercept? This is basically when is the function equal to 0. So that would be when is log base 10 of x minus 1 equal to minus 2. And so this right here is equivalent to saying that 10 to the minus 2 is equal to x minus 1. So this is 1/100th. And so rearranging says that x is equal to 1.01 here. Okay, so some logs and exponential functions on top of our earlier solving inequalities. Lots of good things in here.